So last time we introduced organic chemistry and hydrocarbons in general and said we'd do some of the basics and save the more complicated stuff for future lectures. So today we'll go over some reactions of those hydrocarbons we talked about, molecules that just contain carbon and hydrogen, and we'll reintroduce and do a little more on the unsaturated hydrocarbons. In other words, those that don't meet the 2n+2 rule for hydrogens compared to N carbons. Okay, so let's look at some physical and chemical properties of these simple hydrocarbons first, these things we call alkanes. Just carbon and hydrogen, no other elements present, and it's all single bonds. Okay, so some of the first things I want to tell you is it's insoluble in water. It does not dissolve in water. And why might that be the case? Can you give me a reason?
Water's polar.
Water is a polar molecule or has polar bonds? Which one do you mean?
It's a polar molecule.
Exactly. So a polar molecule, and these alkanes are all carbon and hydrogen, so they contain no polar bonds and are thus nonpolar molecules. So polar molecules do not interact well with nonpolar molecules, so these are essentially insoluble in water. Okay. The next one is, let's say they have lower density than water for the really small ones. So the smaller alkanes of just a few carbons are of a lower density than water. What's the consequence of that?
Lower boiling point, maybe?
Okay, that's one consequence, but the fact that it has a lower density, what physical property or observation would that lead to?
The float water?
Right, so if you mix them with water, or try to, because we said they're insoluble, they would float on top, right? And in the higher density ones, the ones that are much longer than the typical small 5, 4, 3, 2 carbon molecule, so you get 20, 30 carbons in it, those will have a higher density than water, and of course they would sink. Okay? And you already mentioned boiling points, but another point about the boiling point is they tend to increase as they increase the number of carbons. So if I have a n number of carbons and I make it n+1, the boiling point should increase. Now why is that? Well, the molecules tend to stick to each other. It's all non-covalent interactions. So they're very, very weak interactions. But the longer it is, the more of them there can be. So to boil something, you can think of it as, I don't know if you guys remember the show, Getting Voted Off the Island, but you can think of it as one of the molecules getting voted out of the bucket, right? So the ones on the surface acquire enough energy to leave the crowd, right, and release into the air and become a gas. But to do that, you must break all your contacts with all the other molecules. And the more contacts you make with those molecules, the stronger those interactions, the more difficult it is to eject you from the bucket, right, to make you boil. So if you're a longer carbon chain, you can make more contacts. They're not very strong contacts, but a little more if you're a longer chain, and it's harder to release you from that liquid. So for every carbon I add to the chain, I can roughly say it adds 30 degrees, 30 Celsius degrees to the boiling point. So if I add 2 carbons, the boiling point roughly goes up about 60 degrees. And you can use that really rough rule of thumb for all the experiments and all the problems we're going to do in this class. So if I start with a 6 carbon chain and I add 2 more carbons, I expect the boiling point to go up about 60 degrees. Okay, so for really, really short ones, like 1, 2, 3, or 4 carbons, the boiling point is actually lower than the boiling point is much lower than room temperature, we'll put it that way, at normal atmospheric pressure. So if you have a container of, say, ethane or propane or butane or methane, right, those 1 to 4 carbon molecules, then if they're sitting at room temperature, then there'll be a gas. They will already have evaporated because the room temperature is higher than their boiling points. But as you add more carbons, of course, we now have 5, 7, 12, 15 carbons. You add a few more, they stay a liquid at room temperature. And that's because the room temperature, let's say 25 degrees, let's call it, it's pretty average, kind of warm room, but it's a room temperature. That temperature is now below their boiling points, right? They're not yet boiling, right? They're still a liquid, right? And they're not yet turned into a solid, right? So I haven't got them so long that the room temperature they're below their freezing points, right? It hasn't occurred yet. But if I go beyond about 17 carbons, 20 carbons, especially 30 carbons, those are things like tar, where it's got 30 something carbons on it, and at room temperature, it is yet to even melt, right? It's still a solid. Right? So the more carbons I add, its boiling and freezing points increase. Right? Freezing point is the same thing as the melting point, just the point of view of direction. Okay, so really short carbons, really low boiling points, really long carbons, really high boiling points. That's what you need to remember. And the division between the two, when we see it as a liquid, a gas, or a solid, of course depends on the ambient temperature. We'll use room temperature as an example. And it must be really, really short to be a gas at that temperature. If a few more carbons added, it'll be a liquid like gasoline. It's mostly 7 and 8 carbons. There's a few more in there. That's why we call it octanes, because it's mostly 7s, heptanes, and octanes, 8. And then really long ones like tar that you use to pave roads and such is going to be 17, 18, 30 carbons, something like that. It'll be a solid. Okay, so those are all straight chain molecules, just 17 carbons in a row, or 6, or 4, or 1, whatever we were talking about. Now let's talk about if they're branched. Now these are things with substituents, right? They're not just 17 carbons in a row or 6 carbons in a row. It's so many in a row, and it has substituents. It may be some ethyl groups or methyl groups or propyl groups or all sorts of things hanging off of it, but it's branched. And the more I branch it, the boiling point changes. And I want you to think about it physically. I don't want you to memorize it, but if you get the concept down, this will be a lot easier to remember. So if you have a straight chain, let's say 8 carbons, let's just make up one. It'll be 8 carbons long. It'll have a certain boiling point, right? Whatever that temperature might be. I don't know it off the top of my head. But if I were to take that 8 carbon chain, that octane chain, and instead make it 7 carbons long, and take the methyl group that I removed off the end and attach it somewhere in the middle, then it would be a heptane with a methyl somewhere. Same number of carbons, same number of hydrogens. It's an isomer of it, right? It's one of the many isomers of it, but it's a little shorter. And compared to all its friends in the same bucket that look just like it, right, it can't make as many contacts as the straight 8 carbon chain can. Right? So the 8 carbon chains can lay directly side by side and make a lot of contacts with each other. But if I start branching it, and I did one where I had a heptane with 1 methyl on it, but I can make it more branched, of course. I can get really short, only down to 4 or 5 carbons with lots of appendages. Then that thing looks more spherical. It's not as straight and linear as it was before. It's starting to have a problem making a lot of contacts with its neighbors. Do you think that would be easier to boil away or more difficult?
Easier.
Easier. It doesn't make as many contacts, and thus it would have a lower boiling point. It takes less effort to remove it from that bucket. So lower temperature would achieve the same thing. So it has a lower boiling point compared to unbranched or straight chain. And now you can also make the assumption that the more you branch it, the lower that boiling point gets until it's as branched as possible. And that's the lowest that it can get without losing a carbon. But in all those cases, if I remove 1 carbon and just make it 7 carbons long, that will be 30 degrees lower than those. Right? So I'm talking about very fine changes. If I go from straight chain to branched to more branched to even more branched, all those are within usually a few degrees of each other. Right? They're not going to be 30 degrees apart. They're usually 1 or 2 or 5 degrees apart or something like that. Very, very close, but there is a difference. But if I remove a carbon, it drops about 30 degrees. So we're looking at very small changes when you start doing branching. But if I lose a carbon or gain a carbon, it's a drastic difference. Okay. And then finally we have the one that's cyclic, which we haven't introduced yet. We'll talk about it after this slide today. But if I take my straight chain again, let's use our octane example, 8 carbons in a row. And instead of having the 2 carbons at the end having H3s on them, or 3 hydrogens, right? I take a hydrogen away from each one and have the ones at the end interact with each other. So it makes a ring, right? So we have a cyclic chain. There's no start or stop to it. It's just 8 in a ring, right? They're not going to necessarily take on an octagon shape. That's the way we draw it. But it'll be in a ring structure. There's no beginning or end. It's attached to itself. Do you think that will be able to interact better or worse than the straight chain? And why?
Better, because it can kind of tessellate, I think is the word, with other molecules.
So they can interact almost the same way as a straight chain. Everyone will be able to interact with its neighbor, of course. But since it's in a ring, they can form stacks, right? Like a stack of coins. So that's what they'll look like. And that's a better arrangement than just randomly laying next to the other molecule. So this will have a slightly higher boiling point than the same length straight chain. Okay, so if you had to put these in order, more carbons, definitely higher boiling point. Fewer carbons, without a doubt, lower boiling point. But if they have the same number of carbons, right, all these molecules I'm about to describe have the same number of carbons, and our example had 8, then the cyclic one will be the highest boiling point, followed by the straight chain, followed by the just a little branched, followed by more branched, followed by even more branched, right, from highest to lowest boiling points. So cyclic, straight chain, branched, even more branched. Right? But if I lose or gain a carbon, that totally changes everything. It's higher if I gain a carbon than all of those, and it's lower than all of those if I lose a carbon. Okay, so the first thing you should do when trying to evaluate which one has a higher boiling point would be count carbons. Okay. Now let's look at briefly some reactions that these alkanes can do. The most common one we'll talk about will be combustion. And that's simply a euphemism for burning, right? You can think of it burning a molecule. So if a molecule burns or combusts, it's reacting it with O2. So one of these hydrocarbons is just hydrogen and carbon, right? One of these long chains like octane, or it's our example again, or methane or propane. We mix it with O2, molecular oxygen, and we have to provide some spark to get it started, right? And then it always creates the same products. If it's a pure alkane mixed with O2, you always get the same two products, CO2 and water, right? So carbon dioxide and water, and of course this is energetically favorable once it gets started, so it releases an enormous amount of energy, right? And this is how combustion works in your internal combustion engines in your car or a campfire. This is why it keeps burning the wood, because the excess energy released is enough to create the next spark to allow the next molecule to react. And of course it's far in excess, so you get this plasma of heat that's generated, right? So is it endothermic or exothermic? What do you think?
Exothermic.
Exothermic. It's releasing thermal energy, right? We use this, like I mentioned, to create campfires or burn propane at your stove or butane, whatever your stove's using in your kitchen. If you have an electric one, this doesn't work this way. What's the problem this creates? Think globally. What's the problem this could create?
Heat?
Not so much heat, but it's another product here that could be a problem. It's not the water.
Energy? Too much energy?
No, it's not the heat that's generated. There's another molecule product here that could be a problem.
Carbon emission. Carbon.
Yeah, the CO2, right? The CO2.
Excess waste products.
Right, the CO2 can build up in the atmosphere, and it takes quite a bit to do that, but we as humans have done a fairly robust job of creating CO2 over the last couple centuries. And so it's a greenhouse gas. It builds up in the atmosphere and traps more solar energy, which is far more than any energy this reaction could produce. This is minuscule, right, compared to the solar energy from the sun. Okay, so combustion of alkanes always yields the same products. If it's a pure alkane, just carbon and hydrogen, it yields CO2 and water every time. Okay, we'll talk about how to balance those equations when you do it. You probably did that from 1151. Okay, so another reaction we'll do is halogenation. This is an addition of a halogen to a hydrocarbon. Okay, so a halogen is one of your column 7 on the periodic table, the fluorines, the chlorines, bromines, iodines, and so forth. So that next to last column where they want one more bond, right? So we can introduce halogens to hydrocarbons, and we're going to add them across, say, double bonds. Right? We'll talk about those when we get there. Okay, so this is an addition reaction. We're not taking anything away. We're just going to add them to it. But we need a double bond to do that. Right? And the other one, instead of just adding, we could do what's called substitution. Right? This doesn't mean substituent. That's a different type of thing, although they have the same root word. But this is a substitution. I take something away and I replace it with something else. Perhaps I could replace a hydrogen with a chlorine. That would be a substitution reaction. Okay, so we'll talk about those as well. Okay, so let's move on to cycloalkanes and some general properties of these. We said these are the ones that have a ever so slightly larger boiling point than their straight chain counterparts of the same number of carbons, but they don't have the same number of hydrogens. So in this case, if you look at any of these ring structures here, you notice I've taken the straight chain version and connected the ends. But if I'm going to connect the ends, they must not have 3 hydrogens on them anymore. They each had to lose one in order to make this new connection to close the ring. So our general formula for alkanes was CnH2n plus 2. Remember, there's 2 hydrogens on every carbon, and then the 2 on the end had extra hydrogens. So it was 2n plus 2. In this case, we don't have those extras on the end. In fact, in a ring, every one has 2 hydrogens, right? Because they're all connected to 2 other carbons. So our formula here becomes CnH2n, right? And how we get that is we start with the 2n plus 2 rule and realize we were missing 2 because we had to close the ring. So making a ring requires you to subtract 2 hydrogens from your formula. And since we started with CnH2n plus 2, and then we subtract 2, 2n plus 2 minus 2 is just 2n. So don't forget, you always start with 2n plus 2, and then we're modifying it here. If you start with just 2n, you're going to get a lot of wrong answers. So we always start with 2n plus 2, and because I have a ring, I'm going to subtract 2. All right, I'll give you a formula for doing all that later too. So these ring ones are rather easy to calculate their formulas. It's just the number of carbons times 2 is the number of hydrogens. Okay, so looking at the structures, you see I have cyclopropane, cyclobutane, a 5 and a 6 membered ring as well. They can get much larger, but I want you to look at these for a second. And since I've forced them into this geometry, what are the angles on these bonds? Right, so before, when we had all straight chain, so think back to just a regular old butane or hexane or something, right? Not in a ring, just a straight chain. What was the geometry around every carbon?
90-degree angles.
No, remember the geometry.
109.
Okay, so you gave me a couple answers there. The geometry is tetrahedral, right? And the angle was 109.5, right? So the geometry around every carbon in a straight chain is tetrahedral. Why is it tetrahedral? Because it has 4 single bonds attached to it. The carbon on each side and the 2 H's. Right? Even the ones on the end are also tetrahedral because they have 4 single bonds, the 3 hydrogens and the neighboring carbon. But when I put it in a ring here, it's a little different. I want to make one comment before I continue with the rings though. Someone said 90 degrees, and it's a reasonable guess because of the way you're drawing them. Right? You're drawing them on a flat piece of paper and you see a lot of 90-degree looking angles. But keep in mind, the molecule is not flat. It's tetrahedral. It has 3-dimensional volume, right? So those angles aren't what you see on the page. Okay? Whereas in the case of these here, if you draw a triangle, this is a flat molecule, and the angle on this first one would be 60 degrees. Right? So when you make a cyclopropane, that angle at every carbon is 60 degrees between the other 2 carbons. Okay? For cyclobutane, it is what you expect. It'd be 90 degrees. Right? And if cyclopentane were drawn this way, the angle would be 108, and for cyclohexane, it would be 120. However, these last 2 don't look like that in reality. Because I do have a 3rd dimension, when I get to 5 membered rings, they can start bending out of the plane. 3 and 4 membered rings cannot. But a 5 or greater...
I have a question.
Yes, go ahead.
So why is the cyclobutane on this page 90 degrees, but if it's tetrahedral chain, it's 109 degrees? Because isn't tetrahedral still with 4?
So this would, if you had 4 that were not constrained, it would be, and every one of these, all these carbons are still making 4 bonds. Even the cyclopropane is making 4 bonds. But they're constrained. I can't have them form their normal tetrahedral arrangement because they're restricted to being bonded to these other carbons in this ring. Right? I can't move them farther apart. They must connect to the other carbons. I've forced it in this ring. That's why these are 60 and 90 degrees.
Okay.
But to help answer your question, you can also look at the next 2. What I was about to say, the 108, the 120 are not accurate for these 2. If you look at them in reality, right, they're like this, and they try to bend out of the plane. So I'm trying to show that with these wedges here. You may have started doing this in lab with your cyclohexanes. is they don't stay flat like this. They adopt what's called a chair or boat conformation. This is showing the chair conformation. And they actually flex out of the plane of the ring, right? They're not flat anymore. And because of this flexure, they're able to adopt a more tetrahedral looking angle, and they would prefer that, like you said. So because we get beyond 4, we can bend this thing. You notice these 4 are kind of flat, right? And this one is pointed down instead of sticking out flat with the others, right? And that gives you these 109 degree angles roughly. All right, and when you do it with a 6-membered ring, you notice these 4 are kind of flat, and this one puckers up and puckers down. So it gives you that chair conformation. Right, so you'll see that when you play with your model kits, that it's trying to approach 109.5. You're right, it's trying to be tetrahedral. But in the case of these, there's no way to bend it to give you that angle. It's stuck at 90 degrees, and this one's stuck at 60 degrees. So a consequence of that is these ones that are smaller than 5-membered rings, these 3 and 4-membered rings, are very unstable. Right? They're strained rings. They're not happy. They would rather break open and adopt that tetrahedral geometry again. If you get up to a 5 or 6-membered ring, it can approach a 109.5 angle. So it's happy in a 5 and 6-membered ring, especially 6-membered rings. They're very stable. If you go beyond 6-membered rings, they're still sort of stable, but not as stable as, say, a 6-membered ring. But the worst case scenario is a 3-membered ring. Right? So in general, 3 and 4-membered rings are not favored. 5 and 6 are very favored. And beyond 6, it's not wrong to do it. It's not unstable really, but it's not as favorable as a 6-membered ring. So these are the ideal situations to make a 5 or 6-membered ring. Less or more than that is less favored, especially the 3-membered rings and 4. Right? And if you want to see this in action, how it actually works in a molecule, look up how penicillin works. Right? Penicillin has a 4-membered ring. We'll talk about it later in class too. But if you're interested, it has a 4-membered ring, and breaking that ring is what allows it to work. So you had a question?
Yes. So the 5 and 6 ring, they are technically 108 and 120, but they bend to make the most stable.
That's right.
Is that right?
That's right. So when we draw them as a diagram here, showing the regular sided polygons here of a pentagon and a hexagon, these internal angles really are 108 and 120 degrees in these drawings. But in reality, like you just said, they will bend out of the plane in order to achieve a closer to 109 angle.
Okay, thank you.
So absolutely right. Okay. So let's look at some of these, and let's ask ourselves, how many carbons and hydrogens do they have? So we'll start off really simple. Just ask how many they have. The one on the left should seem fairly simple. It's just a 5-membered ring, so it's easily countable. It has 5 carbons. How many hydrogens does it have? Well, you don't want to go counting them. Use your formula. So how many hydrogens would the one on the left have?
10.
Right, so 5 carbons, and it's 2N. But in reality, we started with the formula that you should always remember. It's 2N plus 2. And because we have a ring, like I show here, we subtract 2 hydrogens, one pair of hydrogens. That's what this 1 represents. It's a site of unsaturation. That's what we call it. So for every reason to remove 2 hydrogens, is another way to think about it. So a site of unsaturation, it's not saturated with hydrogens, is another way to say it. I take away a pair of hydrogens for every one of these. A ring is a reason to do that. A double bond is also a reason to do that. We'll talk about these in a minute. But if you think about it, if a carbon and another carbon, a neighboring carbon, are going to make a double bond, they must also each lose a hydrogen in order to accomplish that. So it's another site of unsaturation. And finally, a triple bond, in order to go from a single all the way to a triple, you must lose a total of 2 pairs of hydrogens, or 4 hydrogens. Right? So our formula here is CnH2n plus 2, always start with that. And then for every one of these occurrences, we subtract pairs of hydrogens. So if you have a ring, subtract a pair. If you have a double bond, subtract a pair. If you happen to have a triple bond, you subtract 2 pair of hydrogens. So in this case, our molecule here just has a ring. It doesn't have these other things. So we subtract 1 pair of hydrogens. So our formula, CnH2n plus 2, becomes CnH2n plus 2 minus 2, which that cancels and gives me just H2n. So you're right, it's just 10. for something like that on the left, it might actually seem simpler just to count them, right? But don't fall into that trap, because you're going to get more complex ones like you see in the middle, that it's much harder to count them and you might make a mistake. The math is much simpler. So for the next one, how many carbons do you see? Count all of them.
11.
11, right. So there's 7 in the ring, and then there's 4 outside of the ring, right? The 2 methyls and the ethyl group. Right, so a total of 11 carbons.
Carbon in the middle on the X, like where it crisscrosses, is that a carbon right in the middle?
Yes, there is a
Center?
carbon here. Remember, carbons
Okay.
are at the ends of lines. This one's actually explicitly drawn for you, but they could have just drawn a line here. That would have been sufficient. And,
Okay.
and also there are atoms at every intersection of lines.
Okay, thank you.
So they drew this kind of wide, it looks like this is a straight line, but it actually angles here. And they could have drawn it straight, it would still have an atom there. So all intersections and all ends of lines. Right, so how many hydrogens would this have?
22.
22. And how did you get that?
The 2n plus 2 minus 2.
Right, 2n plus 2 minus 2 because there's a ring. Right, because it contains a ring in the molecule, so we'll subtract a pair of hydrogens. Okay, so good, 22. And the next one? Count all carbons.
I have a question.
Go ahead.
What would the N be when you put it in the formula again?
N is the number of carbons. So it's C sub N, which represents the subscript on the carbon. H, the subscript would read 2n plus 2. And then I do some subtractions depending on features of the molecule. I subtract 2 for every ring, I subtract 2 for every double bond, and I subtract 4 for every triple bond. Remember, these numbers represent pairs of hydrogens.
Thank you.
Okay. So what about the next one? How many carbons?
10.
Is it 10?
It is 10. Right? There's 4 in the ring, 3 in this group, and 3 in this group. And without counting the hydrogens, how many are there?
20.
20.
20. And you got that by the same method. We said we do 2n plus 2, and then there is a ring, so I would subtract 2. So it's just 2n, which is 20. Good. So it doesn't matter where the ring is, whether it's on the end, in the middle, whatever. If there is a ring, then we do this method. We subtract a pair. If there is a double bond, we subtract a pair. If there is a triple
2,
bond,
3, 4, 5, 6, 7, 8, 9, 10.
your microphone's still on. And if we have a triple bond, we subtract 2 pair. What if you had something with a ring and a double bond? What would you do?
We subtract 4.
I'd subtract 4. I'd subtract 2 pairs. 1 for the ring and 1 pair for the double bond. Exactly. And we'll see some examples of those. Okay. So let's move on to finishing our naming rules, because we talked about how to count the carbons and such, but we haven't actually named these things yet. So you know the basic rules. Find the longest continuous carbon chain, right? Rules we did last time. Hopefully you've practiced them. Number it from one end to the other, giving substituents the lowest possible numbers, right? That's all we've done so far. Now we have to introduce how to name the rings. Because our problem here is, where's the end, right? It doesn't have an end. It's a ring. Where do I start counting? So my rule here is, when you're trying to find the longest continuous chain, you either choose the ring or you choose something else. A carbon is either in the ring or it's not. It's never both. Okay, if that makes sense. So if you pick a carbon, it is either a member of the ring or it is not. You can't be in both clubs. Okay? So in the cases below, we want to choose the longest continuous chain that is either the ring or something that is not in the ring. Does that make sense? So let's do a couple examples so you see. I have one of each here. So the one on the left is the longest continuous chain, the ring itself, or one of these things that are not in the ring.
Ring.
Right, how big is the ring?
9 carbons.
9 carbons. If you pick a spot and go all the way around, you'll get 9, not counting them twice. right? So 9 carbons in the ring. How long is the longest straight chain that is not in the ring?
Two.
2, right? So this one's 1, this one's 1. They're just methyl groups. This one is 2, and this one's also 2. You don't count this carbon. You don't count it as 1, 2, 3, because we said this one's in the club of I'm in a ring. So you can't count it as part of a straight chain. All right, so the longest possible straight chain is only 2, which is far less than 9. So we'll name the ring as a 9. Right? We'll get to how we name it in just a second.
Can you repeat that one more time? I'm just confused a little
Okay,
bit.
so when you're trying to decide what's the parent chain, that's what we're trying to decide. We always want the longest continuous chain. But in our case here, we have rings. So how do we choose? There's no start or stop. We either choose the ring itself or one of the straight chains that's on the ring, whichever one is longer. And if it's a tie, it goes to the ring. Okay? So in this case, our ring was 9 carbons around, and our longest piece that's not in the ring is only 2. So clearly 9 is greater than 2. Okay, so our ring is our main chain. Well, we'll get to the wording of it in just a second, but I want you to be able to choose first. All right, the one on the right.
I have a question, please.
Okay, go ahead.
So if let's say we counted and the substituent on it was the longest chain, are we going to count the intersection where it joins with the circle or whatever the shape is?
That's an excellent question, and you lead directly into the next problem. All right, so it's like you were reading my mind. Excellent question. So on the one on the right, right, is exactly what you were talking about. So the ring itself here is how big?
4.
4. And the straight chain attached to it, and this is your question, is how long?
5.
It's 5. You don't count this one. That was your question, right? So you count 1, 2, 3, 4,
Yes.
5. Why don't I count this one as number 6? Because it was in the ring. And this says you're either in the ring or you're not. You can't be in both categories. So this one was one of the 4 in your rings. You can't count it as part of this chain.
Okay, I get it.
We
Thank
have
you.
to draw the line in the sand somewhere. So you're either in the ring or you're not. Excellent question. So in this one, which one is longer?
The one outside the ring.
The one outside. So the parent chain is going to be this 5 carbon chain, not the ring. If this had only been 4, then we choose the ring because a tie goes to the ring. Okay, so let's try to name these two. This is the exact same problems. I just moved them up on the page for you. So the one on the left, you said it was 9. So we're going to call it a nonane, right? Like methane, ethane, propane, butane, pentane, all the way up to 9. 9 is nonane. Okay, it's one of the 10 I asked you to memorize, right? But it's not just nonane. Nonane indicates it's a straight chain. So I have to somehow tell you it's in a ring. So we prefix it with the word cyclo, right? So it's a cyclononane. And that is simply a 9-membered ring. That's all that describes. Am I leaving anything out by naming it cyclononane?
Yes.
What have I yet to account for?
The
methyl.
substituents.
Substituents, exactly. So what are they? What are my substituents?
You have methyl and ethyl groups.
Right? I've got a pair of each, right? I've got 2 methyls and 2 ethyls. How would you name those?
Diethyl and dimethyl.
Diethyl and dimethyl, correct. So the name's going to look something like this, right? And because it's a diethyl, I'm going to need 2 addresses, right? I got 2 pieces of mail to deliver. I need 2 addresses, right? So where are the diethyls and where are the dimethyls? We have a problem, right? Where do we start?
Hard to count.
Yeah, it's hard to count. Where do we start? There's no end. And that's what I'm bringing up with this. You can start anywhere you want on that ring. Any one of the 9 could be number 1. So if you had to guess where number 1 might be, it's probably going to be where one of the substituents is, correct? Because I want to give one of them number 1, right? I want to keep them as low as possible. So I'm going to start counting where one of the substituents is, right? And I have to end by going around the ring either one way or the other. And it's still, I don't know which way to go. So we have a rule for this. When you have more than one thing there, we're clearly going to start counting number 1 at one of those substituents where it's attached, and then go around the ring, but I want to give the lowest sum to all of these. So these 4 locations are going to be at numbers, right? One of them is going to be number 1, and the others are going to get whatever number they get as you go around. And if you try these, you start at each of these 4 places, right? You have 8 options here, right? I'll give you an example. You can start at this methyl group on the right. This will be number 1 here. And you can go clockwise. This would be 2, 3, 4, 5, 6, 7, and the other methyls on 8, and this would be 9. So the methyls would be on 1 and 8, and the ethyls would be on 2, 3, 4, and 6. And then you add up those numbers, 1, 4, 6, and 8, and get a total. You also could start at this methyl and go counterclockwise, right, and get numbers. You could do that at each one of those 4, right? And after a while of doing this, you will see it gets easier. You can recognize right away there's a large gap over here. You probably don't want to start at one of these and go across that gap, because then these other numbers are going to get much larger. Does that make sense? If I start here and go clockwise, these 3 numbers get fairly large. But if I start here and go counterclockwise, they're not so large anymore, right? I don't use these larger numbers. So you'll figure it out after a while that you want to go through all of them with the lowest sum possible. In that case, when you do this, you'll get, starting here at one of the ethyls, right, this one, and going clockwise, you'll get 1 and 3 for the ethyls, and 5 and 7 for the methyls. And that gives you the lowest sum possible starting on here. There is one more option that gives you these exact same numbers, starting here and going counterclockwise. Now the methyls would be 1 and 3, and the ethyls 5 and 7. So they would just switch places. So either one of those is correct, right? The sum
I have a question.
They add up to 16 in every case. So what was your question?
I have a question. So you have to take the lowest numbers for substitutes.
Uh-huh.
You add them up, but you have to take the lowest numbers.
Right. When I'm doing there's a subtle distinction here. When I'm doing a straight chain naming, right? No rings involved, just a straight chain. I want to start from one end that gives me the lowest number to the first substituent. Well, I don't care where the others are. I want to get the lowest number to the first one when I have a straight chain. But when I have a ring, I can start anywhere. So I want to give the lowest sum of all the locations. So there's a slight difference here. Okay, so if I add these up, I get 16. If I started somewhere else, like say the top methyl group, and go either way, I'm getting numbers larger than 16 when I add them. So I'm going to try to keep these to the lowest possible ones. 2 solutions appear, and either one is the correct name. But you also notice we had to alphabetize these. And ethyl comes before methyl. Right? I'm not alphabetizing the dyes, I'm ignoring the dyes, but ethyl comes before methyl. Okay? So these are the correct names for that one. Either one is correct. Right? What about the one on the right? We said which of these is the parent chain? The ring or the straight chain?
Straight.
Straight
The
chain.
straight chain.
So what is the parent name?
Pentane.
Pentane.
It's a pentane, I agree. Is it a cyclopentane?
No.
No, those 5 are not in a ring, right? So I don't name it a cyclopentane. But is it wearing something? Does it have a substituent?
Cyclobutane.
Right.
Yes.
It does have a substituent, and I heard someone say cyclobutane. That would indicate that that's the parent chain, right? Like over here, I didn't call this a methane, or I didn't call this an ethane. What did I do to the word? This wasn't called an ethane. It was called
Ethyl.
ethyl. I changed the ending. I give it the adjective ending, right, instead of the noun, right? We're treating this like a foreign language. So this is the noun. What would you call this as an adjective?
Butyl.
A butyl, exactly. It's a butyl, but it's not just a regular old butyl. It's in a ring, so
Cyclobutyl.
a cyclobutyl. Right, there it is. A cyclobutyl pentane. But it's on my pentane, correct? I need to know where it is. So where is it on my cyclopentane?
1.
It's on number 1. I agree. Right? Is that 1 necessary?
No.
It's not.
It is. Where else could it be?
The other end at 5.
If it's on the other end, it would not be on 5, it would also be on 1. Because then this would be number 1, 2, 3, 4, 5. Remember, I want to give it the lowest number possible. So it could be on 1, attached at either end. It could also be attached at 2 or at 3. It can't be on 4 because that would be the same as 2 from the other end. So I could attach it at 1, 2, or 3, so I need the 1. Absolutely required.
Can you explain the naming again? Like the cyclobutyl?
So pentane down here is my parent chain, right? And on the pentane, I have a 4-membered substituent. Right? So it's got 4 carbons in it. We call it a butyl group. But it's not just a straight chain butyl, it's in a ring, so we call it a cyclobutyl. So this whole thing, cyclobutyl, is the substituent. Right? And then I have to tell you where it is. It's on number 1. And the 1 is necessary, because if I just say cyclobutyl, I don't know where it is. It could have been on number 2 or on number 3. So the 1 is absolutely necessary. Everybody okay
Could
with
you
Question, why couldn't it be on the 4 again?
Okay, so let's say if we try to put it on number 4. So this is, you say this is 1, right? This is 2, I could put it there. 3, I could put it there. If I put it here, what you're calling number 4, right, it's not attached here anymore. It would be on number 2.
That makes more sense.
I want to give it the lowest number
Like,
possible.
okay, you know what I'm saying? Yeah, I don't know what he's saying.
Right, does that make sense?
Dude.
If I start on this end, 1, 2 is where the substituent would be. If I started counting from this end, it'd get a larger number, so I don't want to give it the larger number. When I'm counting, I always want to give my substituent the lower number for the straight chain stuff. So if I put it down here on what you're calling 4 or 5,
I don't know what the fuck it is.
it'd really be on 2 or 1. Okay? All right,
I have a question.
go ahead.
Can you explain when to use methyl
See,
and
look, like
ethyl?
this one.
Someone else has their microphone on. I couldn't hear you.
Can you explain when to use methyl and ethyl?
The difference between methyl and ethyl?
Yes, I'm confused as when to use them.
So over here, when you have 1 carbon as a substituent, right, that's a methyl group. This carbon is in the main chain. It's attached to the ring, right, or it's in the ring. This carbon is attached. This line here doesn't represent an atom. It's just a bond. Right, so this point right here where the lines intersect is one of our 9 carbons in our nonane. This carbon is the substituent. Whereas over here, this pair of carbons is the substituent. The line means nothing. It's just how it's connected. Does that answer your question?
So one line would be
Yes, I can't focus because of the person's speaker on.
Somebody has their microphone open, please.
so would you use methyl? when you have,
Whoever
like,
bubble
one
is,
substituent, or would
your
you
speaker
use
is on.
ethyl?
I'm sorry, say that again?
Would you use an ethyl when there's one substituent like group, or would you use ethyl?
So you use
I'm
ethyl when the substituent has 2 carbons, like this. You use methyl when it has 1 carbon, like this. The reason we're saying
okay.
di, the reason these have a di in front of them is because they occur twice. There are 2 of them here.
Right. Okay, that makes sense. Thank you so much.
Okay, so let me introduce a new topic, and this one's a little more difficult for a lot of students, and it's called cis-trans isomerism. Okay, so you already know what isomer means. We talked about that last time. It's where 2 molecules have the exact same parts. Isomer means same parts, but they're connected differently, right? They're not identical to one another, right? And an example we used last time was if I had, and I also talked about it this time, if I have an octane, 8 carbons in a row, simple straight chain, 8 in a row. I also have another molecule that's 7 in a row with a methyl group somewhere in the middle, right? Those 2 have the exact same formulas. Both have 8 carbons, both have 18 hydrogens. They fit the 2n plus 2 rule. Both of them are identical as far as their formulas go. But they're not the same molecule, right? One's 8 long, another one is 7 long with a methyl stuck on it somewhere. They're not the same thing. They're isomers of each other. They have the same parts, but they're connected differently. That's all isomer means. In the case here, we have a more subtle change. It's called a cis-trans isomer. And this can only occur under 2 conditions, right? Either when you have a double bond, and only certain double bonds will apply, and we'll talk about the rules in a minute, or if you have a ring with exactly 2 substituents on different carbons. That's the thing I highlighted in red here. There's an example down below. So here I have a 6-membered ring, right? It's kind of shown at a sort of a 3-dimensional drawing. It's kind of angled towards you a little bit. Think of a flat hexagon. It's angled towards you a little bit. We know in reality this adopts a chair conformation, but we can draw it like this. So it is a 6-membered ring, and then each of the neighboring carbons in the front there has a methyl group on it. Right? So it's a cyclohexane. The name should make sense. It's a 6-membered ring. That's our parent chain. And then there's 2 methyl groups on it, so dimethyl on this carbon and on this carbon. We're going to call these carbons 1 and 2 because that gives me the lowest numbers possible. But it's the same thing over here. I still have methyls on 1 and 2. But because this is in a ring, right, all 6 of these carbons in a ring, something different happens here. So if I have a normal straight chain, think about it, every carbon-carbon bond in a normal straight chain is free to rotate. Right? I can twist them all I want. Get your model kits out and play with it. You'll see you can rotate those bonds all you want. Right? Spin them around. But if you put them in a ring, you can no longer rotate those bonds. Right? And that's true in reality. These bonds no longer free to rotate. Right? Same thing when we do a double or a triple bond. It is no longer free to rotate. So in that case, if these 2 methyl groups are on a straight chain, imagine this not being a ring, just a straight chain, I can rotate that middle bond all I want. They can be any relationship to each other. You probably did this, you will do this in your first lab where you talk about eclipsed versus staggered versus gauche conformations. Right? But these here, in this case, since they're on a ring and they're both pointed above the plane of the ring, there is no way to rotate this to end up with one below. I can put both of them below and just flip the molecule over. But there's no way to rotate this thing and get one above and one below. So these are clearly different molecules. And we call it, when they're on the same side, either both above or both below, cis. The word cis means same. Right? They're on the same side. Right? Or near each other. Right? Whereas if they're on opposite sides, we call it trans, because it's transversing this plane. Right? It's going across to the other side. One on one side, one on the other. And so to keep these molecules separate, we got to give them unique names. They're still called cyclohexanes. They're both dimethyl cyclohexanes because they both have 2 methyl groups, and they're both on numbers 1 and 2. 1, 2, 1, 2. But we need a new prefix, and we call it cis when they're on the same side, and we call it trans when they're on opposite sides. So you have to visualize your ring and see if there are 2 substituents, exactly 2, no more, no less. If you only have 1, there's no point in asking the question. If you have more than 2, the question becomes meaningless because you can have more than one answer at the same time. So only when there's exactly 2 substituents. They need not be the same thing. One could have been an ethyl, one could have been a methyl, one could have been a chlorine, and one could have been something else. But it doesn't matter what they are, as long as it's not hydrogen. Right? But there needs to be 2
I have a question.
things. Go ahead.
If there are 2 substituents, but it's on a straight chain versus a ring, do you still need to use cis or trans?
No, the cis and trans system only works when you have rings with exactly 2 substituents on different carbons, or if we have some double bonds. Right? We'll talk about the double bonds in a minute. But those are the only situations you're going to encounter. Right? Triple bonds do not count. Can someone guess or tell me why you can't have triple bonds with, or can't have cis and trans with triple bonds? It's okay if you can't. We'll talk about it.
Because they wouldn't be able to have another substituent.
Right. They can't have another substituent. They're already triple bonded, right? Which means if a carbon is in a triple bond, it can at most have one other thing attached. There's no way that they can be above or below anything. It's in a straight line. And if you remember your geometries, triple bonds are linear, right? So there's no distinction. It's straight, right? There's no way you can be opposite or besides, right? So when you have rings with exactly 2 substituents on different carbons, because they can't be on the same carbon, because if they were on the same carbon, by definition, one would be up and one would be down. We would not call that trans because the cis version is not possible. You can only call something cis.
Listed all the time? Like, for example, like I can see from that picture that the 2 carbons are on the same because it's listed. But I mean, like they both look the same. If it wasn't listed, how would I know?
They have to give you some indication, like a drawing like this, or to say one is up and one is down, or so forth.
Okay, perfect. Thank you.
When we get to the double bond ones, it's a little more obvious. Yes?
I have a question real quick.
Go ahead.
So in lab, when we talked about cis and trans, they also used E and Z as kind of being synonymous. So could you also use E and Z to describe rings?
So when you have things like pairings like this, cis versus trans, or there's several other systems, like you mentioned E versus Z. There's one that's R versus S, and there's a D versus L. We'll talk about a few of those later, but for this we're going to stick to just cis and trans. Okay, we'll actually use the D and L system later when we get to carbohydrates, but we'll review what we just talked about today. But we'll stick to cis and trans for this today. Right? So I'll talk about the double bond cis and trans a little later. I'll give you the rules for that, but I want you to remember the rule for this one was exactly two things on a ring, exactly two substituents. Their identities don't matter as long as they're not hydrogens. Right? They don't have to be the same, but they must not be on the same carbon. So exactly two, no more, no less, right? And on different carbons. They don't have to be side by side. If I go back a second, one could have been here on number 1, one could be over here on number 4, or on number 3. It doesn't make any difference, as long as there's two. Okay. Right, let's finish up with a few other reactions for today. So this is my halogenation reaction, right? So this is my replacement, right? I'm going to replace one substituent with something else. So in this case, we're replacing one of the hydrogens on this carbon with a chlorine. And the way you do this reaction is you take methane or any other hydrocarbon. So methane works really well, right? Just one carbon with 4 hydrogens on it. We add diatomic chlorine, so chlorine gas. And we have to give it some energy to get this started. So we either heat it up to 400 degrees Celsius or something, or blast it with some UV radiation, but some energy input to get it started. And what happens is one of these chlorines replaces the hydrogen on here. Now keep in mind this Cl2 is a chlorine bound to another chlorine, so you could draw it that way as Cl-Cl. And what's happening is these two molecules are switching partners, right? The chlorine is bonding to the carbon, and the hydrogen is now going to bond to the other chlorine. And you see they've swapped places here. So we now have a chlorine-carbon bond, and the H that was on here is now bonded to the other chlorine as HCl. But as you remember, HCl isn't going to be a covalent bond. That's a very strong acid, and if you remember the electronegativity difference, it's great enough to be an ionic bond, hydrogen being 2.1, chlorine being closer to 3, 2.9 to 3. So this is large enough to be an ionic bond, and HCl being a strong acid will lose its proton immediately and become Cl- and H+. And that kind of drives this reaction forward. So this is halogenation. I'm replacing, right? I'm not adding, I'm replacing. This is substitution. One chlorine for one hydrogen. Okay? So if you were to write the formula of this, you'd write methane as CH4. That still fits my formula, right? The 2n plus 2 rule, or n being 1, right? But over here, it doesn't fit the rule anymore, right? There aren't 4 hydrogens, but the chlorine has taken the place of 1. So in our rule, when we write CnH2n plus 2, if you see any halogens, which are fluorines, chlorines, bromines, iodines, all those in that column, we generally represent it generically as an X. If you see any halogens, then for every halogen, you need to subtract 1 hydrogen because it took its place. Right? So in this case, our formula still is CnH2n plus 2 minus 1 for that chlorine. And then you would get 3 as your answer for a number of hydrogens. Right? So for every halogen you see, and this is the way we add the halogens, this replacement or substitution, then for every chlorine or bromine or iodine or fluorine, you subtract 1 in the formula for H's.
Can you repeat what the formula will be?
So we're going to put it all together later, but for this particular example, it always starts C sub n, H sub 2n plus 2. You always start with that. And you already know for every ring you subtract 2 hydrogens, for every double bond you subtract 2, for every triple bond you subtract 4, and for every halogen you subtract 1, because it took the place of 1. Does that make sense?
Yes.
So the final one will be 2n plus 2 minus 1?
Correct.
Okay. Okay.
And if I had 3 chlorines on this thing, you would be 2n plus 2 minus 3. You subtract 1 for every halogen. And that should help you do a lot of the practice problems. But how that halogen, chlorine, fluorine, bromine, iodine, got there is by this replacement method. So it's been substituted. It took the place of one of the hydrogens. And that should explain the formula. Okay, so here's an example. Right, so let's walk through this one together. I want to name this thing. Right, so it has a certain number of carbons there. It has so many hydrogens there, and it also has some chlorines there. Right, and we have to explicitly show the chlorines because you won't know otherwise. But we treat the chlorines as we would treat any other substituent. Right, so if you had a methyl or an ethyl or a propyl group on there or a cyclobutyl group, or we've done all those examples today. So if you have any of those substituents on there, you just treat it as a substituent, right? Ethyl, methyl, give it a location. But we do that with chlorines and bromines and iodides as well. So this is just called a chloro group. That's the adjective form of chlorine. Just say chloro and give it a location, right? So let's try this one. So the first step here would be to count what?
Chain.
Find the longest continuous carbon chain. What do you get?
4.
4, right? So it's 1, 2, 3, and 4. These are not carbons, so don't count the chlorines. And the bonds are not atoms, so don't count lines. You want to count carbons. So this is not a carbon. This is the first carbon, or if you're starting from this end, this is the first carbon. Either way, you're going to get 1, 2, 3, 4. Okay? So far we have butane. This is not 6 carbons long. I see that all the time on tests. Right? So don't count these as carbon because they're not. They're chlorines. Right? So 1, 2, 3, 4 carbons. It's a butane. What's on the butane? Well, let's circle our butane. If you had a pencil, go ahead and circle these 4 carbons, right, in a little like worm-shaped thing there. And that leaves my substituents unaccounted for. So I need to account for substituents. Just like you would with a methyl group. What do I have?
Methyls.
I have chloros,
4.
right? I don't have methyls or ethyls here. I have chloros. How many of them?
4.
So how would you name that?
Tetrachloromethyl.
So they're not methyls. They're just
Tetrachloro.
chloros. There's no carbon here. This is a carbon here in the main chain, 1 of 4. There is no carbon up here. It's just a chlorine attached. Right? So don't call this a methyl. It's a chlorine. That's it. So it's a tetrachloro. Right? So tetrachlorobutane. There are 4 of them. And then, of course, I just tell you where they are. They're on numbers 1. This is on number 1, right? 2, 3, and 4. There they are. Okay. Do I need these numbers? Do I need 1, 2, 3, 4? Or is tetrachlorobutane sufficient?
Yes.
I do need the numbers. Why?
Because you could have more than one chlorine on the same substituent, the same carbon, or the same carbon.
Yeah, I could have put them elsewhere. And in fact, this carbon, let's look at this one here, for example, has room for another chlorine because it could take the place of the one hydrogen that is there. That would be a different molecule. It would still be a tetrachlorobutane if, let's say, this chlorine wasn't here and there was one here, but they would not be on 1, 2, 3, 4 anymore. Right? So the other options exist. For example, they could be on 2, 2, 3, and 3. So take this one off and put it here. Take this one off and put it there. That would be a 2, 2, 3, 3. We could also have 1, 2, 2, 3. Well, this one's here, 2 here, and 1 here, and none on the end. But certain combinations are not possible. Like 1, 3, 3, 4 is not possible. Can someone tell me why?
Because it would just be 2, 2, 3, because it would be flipped.
It'd be on you counting from the wrong end, correct. So instead of 1, 3, 3, 4, we count from the other end, and it would be 1, 2, 2, 4.
And you said that we don't count it or say it as methyl because it's not a carbon, it's its own element?
Yes, that's correct. It's not a methyl group with a chlorine on it. That's not the case. It's just a chlorine.
Thank you.
Right, you're absolutely right. If it were a methyl with a chlorine on it, for instance, if all of this were somewhere else and you had just this carbon chlorine as a substituent, I know it's not in this case, but if this piece were a substituent, this whole thing I'm outlining here, then it'd be a carbon with a chlorine on it. right? That would be named differently. That would be a chloromethyl. But in this case, it's not. This is part of the main chain. So the only substituent here is the chlorine atoms themselves.
How did you count 1, 2, 3, 4?
Okay, so number 1 right here, or number 1 right here, whichever side you'd like to start from. Right, so 1, 2, 3, 4. These are not carbons, and lines are not carbons. Only at intersections are atoms. So 1, 2, 3, 4. So that's what I wrote down here. Don't count the chlorines as carbons, and don't count the lines as carbons. That's very common mistakes I see people make.
Professor, I have a quick question.
Go ahead.
So it could be any other halogen too, and we would just say, like, instead of chloro, we'd replace it with whatever it is. We wouldn't add the, like how ethyl has L, like the YL at the end.
So
we wouldn't add that ever if it's a halogen. Right.
So the names are just chloro, bromo, fluoro, iodo, and so forth. Right? But I think you talked over some other person who's asking a question.
I'm sorry.
Yeah, why would it butane be butyl? I'm just trying to make sure I get my name on point.
I'm sorry, I couldn't hear your question.
Why wouldn't butane be butyl?
Because butane is the parent chain, right? So when you're writing out these names, just like with a normal language, if you're describing a noun, right, you list the noun, and then you have a bunch of adjectives, right? You don't turn the noun into another adjective. So here our parent name always ends in the noun ending, in this case ane, because there's no double bonds or anything. And then everything else is a substituent. Just like in our previous examples, we had the cycloalkane. Then it had the ethyls and methyls on it. We didn't change the ending to octyl because it was the parent.
Okay, thank you so much.
Okay, moving on to the double and triple bonds real quick. We'll introduce those one more time. All right, so here we have on the bottom left, we've seen this figure before. There's an ethane, an ethene, and an ethyne. And I want to go over the nomenclature this time. So in the case of the double and triple bonds, you notice all we change is the vowel. Ethane becomes ethene, A to E, and ethene becomes ethyne. And I'm purposely exaggerating the vowel sounds so you hear them. So ethane, ethene, and ethyne. Sometimes it's said quickly and you hear ethene. You're like, what did you just say? Was it ethene or ethyne? I couldn't tell the difference. So I'm purposely saying them slow and exaggerating it so you can hear it during the lecture. So if it's an A, it means there's a single bond. E indicates a double bond, and the Y indicates a triple bond. Okay? So that's as simple as it gets. That's all we're doing is changing these. Okay, so I want you to somewhere on a notebook or a back of a page or make a new sheet or somewhere, I want you to start making a list, and we're going to call it our priority list. Okay, so somewhere on a piece of paper that you're going to save for the rest of the semester, I want you to make a priority list. And we're actually going to build this priority list from the bottom up. So of the least to most priority. So start at the bottom of your page. Right, so our first one at the bottom, write hydrogen. It has the least priority of anything. And in fact, we ignore it completely. That's how low priority it is. So it certainly goes on the bottom. We generally just ignore it. Right above hydrogen, I want you to write everything else. Just write the words everything else. Because if it's not in our list above it, it'll be in this little category called everything else. Okay, and right above the words everything else, in the next highest category, write double bond. Okay? So that means a double bond has higher priority than everything else, as far as you know right now. Okay? And then underneath all that is hydrogen. All right? I guess I should have told you the next one first, because you're going to have to erase, I guess, if you did it in pencil. Triple bond is in fact not higher priority than a double bond. It's lower. So it goes just underneath double bond in your list. So from bottom to top, you should say hydrogen, everything else, triple bond, double bond. That's bottom to top in your priority list. So top to bottom would be double bond, triple bond, everything else, hydrogen. Sorry if I messed up your fancy, pretty list. Right, but we'll build onto the top of this as we go. But for now, those are the ones we're interested in. Okay, so a double bond is your highest priority thing so far, followed by a triple bond, and then everything else is of equal priority. And when I say everything else, I mean things like ethyl groups and propyl groups and methyl groups and chloros and bromos and everything else you can think of right now that we've studied. Right, we'll add to the top of our list later as we introduce them. But for the ones you're going to see right now, double bonds are the top of the list. Okay? So when I ask you to find the longest continuous carbon chain, which was rule number 1 every time, we now have to put some caveats on that rule. We have to put it in priority. So if I say find the longest continuous carbon chain, and you see a double bond in the molecule, that double bond must be in that chain. Even if it's not the longest overall, it must be in your longest chain. So we look at priorities now. Okay? So let's do a couple examples of these, and I'll show you some pictures. Right? So here's some rotating graphicals of these different shapes we've seen. So at the very top, you have your simple double and triple bonds. Ethene is our simplest double bond, and acetylene, or the proper IUPAC name for acetylene, is ethyne with a Y. And you see it's linear. The acetylene molecule there is perfectly straight. It's linear. Whereas the ethene has what geometry around those carbons? This molecule here. These carbons here have what geometry around them?
Trigonal planar.
Trigonal planar. And beyond just knowing the words, the second part of that, planar, tells you that it's in a flat plane. And you can see they're rotating that flat plane towards and away from you. So all 4 of those hydrogens that you see attached and the 2 carbons, all 6 atoms, lie in a flat plane. And that's what they're rotating towards and away from you. Right? And of course you said it was trigonal planar, so the geometry is a triangle. Right? So you see these form a triangle here, 120 degree angles between each one. Whereas on this one, it's 180 degrees. They're in a straight line across here. Okay? The next one on the middle on the left is a plain old 5 or 6, I think I drew, a 6 carbon molecule. Right? So plain old 6, what name would it have?
Hexane.
Just hexane, right, exactly. Just plain old hexane. And you notice we tend to draw it with that up and down zigzag line, and it really does look like that, right? The hydrogens, however, are not in the plane where you keep drawing them. Earlier on, someone had said it was 90 degrees, but if you look at this thing, you notice they're not pointed directly up and down if you put the zigzag line flat on the page. One of them's coming towards you, one of them's kind of coming away, and it has that shape. And if I pause it right when we do that, you'll see if I draw this zigzag line like you've been doing, these hydrogens are not pointed up and down. They're kind of coming out towards you and fading away from you. So this is a tetrahedral arrangement. It's not flat. Okay, so keep that in mind when you're looking at these.
So the ethene, the 2 at the top, the ethene would have a higher priority than the one on the right because it's a double bond?
Correct. In the naming scheme, double bonds have a higher priority than triple bonds. That's if they both occur in the same molecule. So if a molecule had both a double and a triple bond in it somewhere, the double bond takes priority. If there are no double bonds, then a triple bond is highest priority over everything else like chlorines and methyl groups. Okay, let's look at the next one, the one below it down here. Right, that's a cyclohexane, and you notice it's not perfectly flat. It isn't a hexagon. It has that chair conformation to it. And if you look at it, you'll notice that the hydrogens are not pointed up and down directly. They're kind of have 2 versions. They're either pointed, let me freeze it for you and show you. Right, they're either pointed directly above the ring or directly below the ring for these. And then the ones on the sides are pointed outward, right? They're kind of pointed, not straight out, they're either slightly up or slightly down, right? And you learn these when you get to the lab. They're called the axial conformations, pointed up and down, and the equatorial conformations, which are pointed almost straight out, but not. They're slightly up or down. And the key here is the ones that are pointed slightly up or straight up are on one face of the ring, and the ones that are pointed straight down or slightly down in the equatorial are on the other face of the ring, and they will never change sides of the ring. They're either on one side or the other. Right? And that's why these rings are you can have cis and trans with these because they can't rotate these bonds, whereas all these are free to rotate. The double and triple bonds obviously can't rotate. So the one here on the right, in the middle, is called trans 2-pentene. Right? Now, why did I call it trans? Let me freeze it and I'll show you. Right, so here, it's kind of hard to see the double bond. There you go. So here's your double bond in the middle. So there's 1, 2, 3, 4, 5 carbons. There's pentane. I changed the ending to pentene because there is a double bond. Right? Remember, we changed the A to an E. And why is it on number 2? Because if I count from this end, I get 1, 2, which I'll talk about that in just a second. But if I started on this end, the double bond would get 1, 2, 3. I go for the smaller number, so I give it to 2. This is 1, 2, 3, 4, 5. And I'm calling it trans because these two, this side and this piece, are on opposite sides of this ring. Right? If this end carbon had been up here where this hydrogen was, instead of out here, because this can't rotate, that would be different. This would have been cis. And we'll talk about that on the next slide. Okay? And then finally at the bottom is a 2-pentyne. And this one confuses students sometimes. It's often hard to count because when you're drawing these things, like the hexane over here, you like drawing these zigzag lines. But when you have triple bonds, as you see at the top, they're straight. So in this case here, if I pause it for you, you notice 1, 2, 3, 4, 5. These 4 are in a straight line because the geometry about these two carbons involved in the triple bond is linear. So it's 1, 2, 3, 4, 5. So when I draw this on the page, I will draw these 4 carbons in a row with a triple bond between the middle ones. So don't count it as 1, 2. It's actually 1, 2, 3, 4, 5. So make sure you count all the carbons. Right? And it will be often drawn as a straight line because it is linear. Okay. So here's a whole block of text with a bunch of rules on it. You know most of these already. I just want to point out the differences. Right? It's basically your rules from last time. I just repeated them. But I want to talk about if there's an unsaturation. In other words, I have a double bond there. Right? Or a triple bond. But let's talk about double bonds first because it's the highest priority. Right? So if your longest continuous chain that you find must contain the double bond because it has priority. Even if there's a longer one without it, we must include the double bond in the longest possible chain. We change the ending from ane to ene. That's rather simple. Right? And then I have to tell you where the double bond is located. So I give it the lowest possible number. This numbering scheme where I choose one end over the other to give the double bond a number, like I showed you on the previous slide, where I gave this end number 1 versus this end to give the triple or the double bond here the lower number is because it has priority. Priorities matter. Substituents like methyl and ethyl groups and chloro groups and all that are down below this in the priority list, so we ignore them for now. Right? So we give the double bond the lowest possible number because it has priority. Right? Once we give the double bond its possible lowest number, everybody else gets what they get, or gets what they get, because it's not a priority. If you're not highest priority, there's no trophy for second place. You simply get what you get. Okay? So we name all the other substituents, give them their numbers and so forth, and Greek prefixes if they need it, if it's di or tri methyls or something. Right? And that's how we prioritize double bonds. If there is a ring, right? We talked about this already. If there's a ring, right? The cycloalkane, right? Just a normal ring sitting there with a number of carbons in it. You can put number 1 anywhere you'd like, right? And you use these substituents to help you figure it out. We did a couple examples. But if you have a ring with a double bond, it's not a cycloalkane anymore, it's a cycloalkene, the double bond still has priority. So if you have a ring, we could have thought about putting number 1 anywhere, but if you have a double bond, the ring with a double bond in it, one of those carbons of that double bond must be number 1. And of course, the other carbon will be number 2. So it must go through the double bond. We'll look at some examples in a second. Okay? Once you've established that, all right, then the ring has 2 options. You could go around the ring in one of 2 directions, right? Because the double bond has 2 carbons in it. One could be number 1, the other is number 2. So do you go clockwise or counterclockwise? Then we look at our substituents again and go which way gives us the lowest number to the first one, right? Much like we did before. We're not interested in sum for this one. The lowest number to the first one. Okay? If there's more than one substituent, then we look at lowest possible numbers again. And let's put all these rules aside real quick and do some examples. It's easier to learn by looking at examples. Okay? So here's a bunch of examples. Okay, so the top left one, let's try that first. There's no ring here, but there is a double bond. So I want to find the longest continuous chain that must include the carbons of that double bond. That's fairly easy for this one because it's all the carbons. So what's the parent name for this one on the top left?
Hexene.
So let's start out simple and build it. So it's 1, 2, 3, 4, 5, 6. So hexane. But you said there's a double bond. I agree. So we change the ending to hexene. And where is the double bond?
2.
It's on 2. I know it involves carbons 2 and 3, but we give it the number of the first one, 2. If you count it from this end, it would be on 1, 2, 3, 4. Counting from this end, it's on 1, 2. 2 is lower than 4, so I'm going to start counting from this end. So it's 2-hexene. Anything else you'd like to tell me about it? It's trans. How did I get that? So here's the rule for cis and trans with double bonds. We already talked about the ring ones, but let's talk about the double bond ones. What you do is you draw an imaginary line, right? You can make it a dotted line to make it easier. Imaginary dotted line along the length of the double bond, right? So along here, draw a line, right? Not this direction, but along the length of the double bond, right? Draw an imaginary line there, okay? And then I want you to ask yourself, the things attached on this end, since it is a double bond, it has 4 bonds on this carbon, 2 of them to the other carbon. That leaves me 2 more. What are the other 2 things attached here? One of them is a methyl group, right? One's a single carbon. And the other thing not shown is a hydrogen, right? You ask yourself, are these 2 things different from each other? A methyl group and a hydrogen. Are they different? Yes, right? One's a methyl, one's a hydrogen. They are different from each other. You've passed the first test. Move to the other side. Are these 2 things, well, this is a long 3-carbon chain attached here, and a hydrogen again. That's the 2 things attached on this side. Are those 2 things different from each other? Yes. One's a hydrogen, one's a 3-carbon group. Right? Look at the whole thing. They're also different from each other. If you answered yes to both of those, if this side had differences, and this side has differences, then you can ask the question, it is cis or trans, which one is it? If these 2 things are the same, then it cannot be cis or trans. Or if these 2 things are the same, it cannot be cis or trans. So the first question you always ask is not, is it cis or trans, is can it be? Right? And we check for differences. These 2 are different, these 2 are different, then it can be. Now the question becomes, is it cis or is it trans? Well, back to our imaginary dotted line. If I imagine it again, it's around there, and I go along the main chain from here to here, did I cross that line? I did, right? The imaginary line was here, right? And if I go along the chain, I definitely crossed it. In other words, I went here and didn't end up back on this side. I went that way. Had I gone this way and ended up back this way, it would have been cis, right? But I definitely crossed it, so it's trans. We'll see some other examples in just a minute.
You said trans and cis can only happen when?
So cis and trans happen when you have a ring with exactly 2 substituents, no more, no fewer, and they're on different carbons. Or when you have double bonds that meet the criteria I just laid out. We have a double bond and it has differences on this side, differences on this side, and then you follow the main chain to say if it's cis or trans.
After class, can you like on Discord, can you just post like a drawing of that, like the imaginary line? I'm just not seeing it. I understand what cis and trans are. I don't see it.
Yeah, I can do that after class.
Thank you so much.
Okay, let's look at the rest of these since we're running out of time for class and finish up this page. So the second one here, what would you call the main chain here? How long is it?
Butene.
It would be butene. How'd you get butene?
The double bond is part of the parent chain.
Right, the double bond must be in the main chain. So I can't go across here skipping that double bond and say 5. That's not possible. I must include it. So I must include these 2 carbons in the main chain. right? And I also must start counting where? Which end is the end? Which end's number 1?
The one closest to the double bond.
Which one's that?
The one that starts with the double bond.
How about right up here at the top?
Yeah.
Right, this is number 1. Because then I can get 1, 2 as my double bond. I can't get a lower number than 1 for a double bond. So 1, 2, then you can go left or right and get the longest chain. So I'm going to go left. 1, 2, 3, 4. You could have gone 1, 2, 3, 4. Same thing. All right, so I have a butene. I agree. And what's on the butene if you circle all that?
An ethyl?
An ethyl group. Where is the ethyl?
On 2.
On 2. So here's my name, butene. I told you the double bond is on number 1 because I had to do that. And then there's an ethyl on number 2. So this 1 here indicates the position of this ene of the double bond, and the 2 tells you the position of the ethyl. Okay? So you guys work through the rest of these, and I picked these 6 examples for a reason. I want you to learn something from each one of them. Okay? The one on the top right is quite difficult, so I'll let you try that one on your own. It's got a lot of features to it. And the 3 down here also have something new to introduce to you. All right, so I'll leave those for you to do on your own. Right? Don't look at the answers now, but go through them. And then the other thing I want you to do on your own with the rest of these slides is if I give you the name, I want you to redraw it. We did a couple of these before. Here's a name. You should be able to draw. It may not look like mine, and that's okay, but draw it. And then once you finish drawing it, is it correct? Or if it's not, rename it correctly. So go through those, and I did a couple examples here. Okay. After that is a few more definitions and some biological relevance for these that I want to go over later. Okay. So you guys can stop here, work on some of those on your own, and we'll pick up here next time.